Welcome to The Explainer. So today, we're actually putting on our detective hats. You know, we often think of chemistry as just this bunch of dry, boring equations on a chalkboard. But honestly, it's really more like a quirky, high-stakes true crime investigation into the invisible rules of the universe. We're going to track down missing mass, uncover some pretty wild ancient recipes, and literally reveal the microscopic puzzle pieces that make up, well, everything around us. Let's get into it. Okay, let's dive into this with our very first mystery. When something burns, where does the mass actually go? Think about it. Have you ever watched a massive log burn in a campfire? It starts out super heavy and solid, right? But by the end of the night, it's just this tiny, feather-light pile of ash. Did the matter just magically vanish into thin air? I mean, it is the ultimate locked room mystery of the natural world. To solve this, we really need to set up a basic crime scene using a simple physical change. We're going to pour some water into a beaker, add a scoop of regular salt, swirl it all around until it completely dissolves, and then record the total mass. What we're doing here is basically establishing a baseline, a scenario where we can clearly see if anything, actually goes missing. And look at that. Before and after the salt dissolves, the digital scale reads exactly 55.01 grams. So, in a physical change, the mass of the solution exactly equals the sum of its ingredients. The salt might be hiding from our eyes, but it definitely hasn't fled the scene. It's got a perfect, rock-solid alibi. But wait, let's make things a little more interesting. What happens when we trigger a chemical change? If we mix vinegar and baking soda in an open flask, we get this crazy fizzing, bubbling reaction. But when we check the scale afterward, the final reading doesn't match the initial reading at all. Some mass has mysteriously disappeared. Why? Well, because our prime suspect, carbon dioxide gas, took full advantage of that open flask and made a run for it. So how exactly do we catch a fleeing gas? We use a balloon, like a giant microscopic police net. By sealing the conical flask with this green balloon, we perfectly trap the carbon dioxide as it bubbles up from the vinegar and baking soda. And boom, the digital scale reads a rock-solid 22.140 grams. We've just proven that when the system is closed and absolutely nobody can escape, the mass stays exactly the same before and after the reaction. Which brings us to a brilliant absolute truth uncovered by our very first master detective, Antoine Lavoisier. Known as the father of modern chemistry, Lavoisier was basically the ultimate chemical accountant. He stated that in every operation, an equal quantity of matter exists both before and after the operation. He essentially realized that nature never, ever cheats on her taxes. The universe balances its books perfectly every single time. And this massive realization led to a foundational rule in chemistry: the law of conservation of mass. It literally states that matter can neither be created nor destroyed in a chemical reaction. Lavoisier proved that the universe keeps this perfect, meticulous track of all its atoms during any chemical caper. The total mass of the reactants will always, always equal the total mass of the products. Mystery number 1 officially solved. With the case of the vanishing mass closed, it is time to open a new file. Case number 2, the universal water recipe. And this brings us to a really fascinating question. Okay, so we know elements combine to form compounds, right? Like hydrogen and oxygen getting together to make water. But do they just throw their ingredients together randomly? Are they like a chaotic chef just tossing spices into a pot and hoping for the best? Well, the answer is a resounding no. And the vital clue here is a remarkably simple ratio, 1:8. It turns out that whether you scoop water from a rushing river, pump it out of a deep bore well, or purify it from the salty ocean, pure water perfectly clones its recipe every single time. It is always exactly 1 part hydrogen to 8 parts oxygen by mass. So if you decompose 9 grams of purified water from literally anywhere on Earth, you will always get 1 gram of hydrogen and 8 grams of oxygen. No exceptions. This brings us to another brilliant chemical detective, the highly meticulous French chemist Joseph Proust. He cracked this particular case and proposed the law of constant proportions. This law tells us that in any compound, elements combine in a fixed ratio by mass, completely irrespective of where they came from. It turns out nature is an incredibly strict baker who never, ever alters her recipes. Now, what's really interesting about this next piece of evidence is this bright red chunk of rock. This is cinnabar, which was known in ancient India as hingula.
For centuries, it was widely used across all sorts of ancient civilizations as this vivid red pigment for painting. And just like water, this rock holds another, perfectly fixed, totally unchangeable recipe hidden inside its vibrant color. Ancient civilizations discovered that if you heat cinnabar, it breaks down into two elements, precisely 86.22% mercury and 13.78% sulfur by mass. I mean, it really doesn't matter where on Earth you mine this stuff, that exact, incredibly specific ratio is locked in by the very laws of the universe. It's just wild how consistent it is. Now, I need to issue a giant flashing warning right here. Do not try this at home. While those ancient civilizations figured out that you could actually artificially create cinnabar by grinding mercury and sulfur together in this exact fixed ratio, doing so is a terrible, highly toxic idea. Both mercury and sulfur have incredibly toxic natures, which honestly, thankfully, prevented this process from becoming too widespread. We're definitely going to leave the poisonous rock recipes to the history books.
Okay, let's move along and see how this all builds up. All of these clues perfectly set the stage for our final detective, John Dalton. Dalton looked at Lavoisier's conservation of mass and Prost's constant proportions, and he stepped right in for the grand reveal. He needed a scientific theory that could logically explain exactly why substances combine in these fixed proportions and why there is absolutely zero loss or gain of mass during a reaction.
And here is his brilliant deduction, Dalton's atomic theory. He boldly postulated that all matter is made up of incredibly tiny particles called atoms. Furthermore, he realized these atoms are completely indivisible and indestructible, meaning you can't create them, you can't destroy them, and you definitely can't chop them up during a chemical reaction. And finally, he proposed that atoms of different elements combine in ratios of simple whole numbers to form these perfect compound recipes. Guys, this right here is the massive eureka moment of our whole investigation. Atoms are essentially the universe's microscopic puzzle pieces. Dalton proved that in chemical reactions, mass isn't mysteriously vanishing into the ether, and those perfectly portioned compounds, they definitely aren't a coincidence. Atoms just detach and rearrange themselves to form completely new substances. The puzzle pieces stay exactly the same. They just snap together to form a brand new picture. But as with any truly great true crime investigation, solving one mystery really just kicks open the door to another. So I'm going to leave you with this bit of a cliffhanger. Are there any chemical changes out there that do not obey the law of conservation of mass? Like, are there actual rule breakers in the universe? Keep that inner detective hungry because this quest is far from over. Thanks so much for joining me on this atomic investigation, and I will catch you in the next explainer.